I want to begin the second part of circuit analysis for RL, RC, etc. type circuits, where we are now looking at what we call the transient or time-dependent behavior of the circuit, which means we're going to kind of transition from physics into calculus. But first I want to review. Again, just to be clear, at time equals 0 on this first circuit, if we switch the switch to A, at time equals 0, in part A, let's be clear that the current going through the resistor initially is just going to be the voltage divided by that resistance, since the capacitor acts as a wire at time equals 0. So that's just going to be 20 divided by 2000, which is going to be 0.01 amps. And then at time equals infinity, as t goes to infinity, what's going to happen is that the capacitor gets filled up with charge, and there will be absolutely no current going through the circuit. So that means I is 0. Finally, at t equals infinity, the voltage on the charge on the capacitor, we're going to use Q equals CV, which is going to be 4 microfarads times 20 volts, which gives us 80 microcoulombs of charge. So now what we want to do is set up the differential equation when we switch the switch to B. So what that means is we have negative voltage of the capacitor minus the voltage of the resistor equals 0 when we switch the switch to B. Because what happens there is that we basically have an RC circuit with no battery. We have a fully charged capacitor. It's going to discharge through the resistor. So to kind of be clear on what the physics of this is, we're basically going to have something that just discharges. In real life, if you think of a battery as, if you think of a light bulb as being a resistor, if you were to hook it up to a capacitor, you'd see it glow really brightly and then start to dim as time went by. So that's going to be negative Q over C minus IR equals 0. And the differential equation we're eventually going to solve is negative Q over C minus dQ dt equals 0. So one thing we should kind of notice here about this differential equation. Notice it's got a dq dt, and I need to add the R for the resistance right here. And the thing I want to note right here is, first, there's the derivative of Q, and then there's Q itself. This is a very important class of differential equation that we encounter in AP Physics, and it's going to pop up again where you have a function and its derivative in an equation. In fact, the most common way I could say this, it's that we have, it's like we have a constant times a function plus another constant times the derivative of the function. Now, I know in calculus class you're used to seeing derivatives written as f prime, but this is a time derivative, so we use dots instead. And that equals 0. So this is kind of the general form of this equation. And this is the class of differential equation we're going to learn to solve today. So this is kind of the first page. I'm literally going to repeat this argument on the next page when we go ahead and look at the RL circuit.